The last trig function that we're going to work on graphing is the tangent of theta. Now, graphing the tangent of theta is a lot more work, I'm not going to lie, because you have to know, remember, go back to tangent, you know how tangent theta equals opposite over adjacent, or in this case, again, when the hypotenuse is 1, that opposite side and adjacent, opposite side is the sine of theta, adjacent side is the cosine of theta. So therefore, to find the tangent of theta, it's the sine of theta divided by the cosine theta. So when we use these unit circle values, so if I want to find the tangent of 0, well, that's the y divided by the x, 0 over 1, which of course is just 0. So that's a nice easy one. But then if I do this one here, the tangent of pi over 6, that's the sine of theta, which is a half, divided by, I'm just going to use the divided by sign, the cosine of theta. So we change division into multiplication by the reciprocal. We've done all this. This isn't anything new. We get 1 over the square root of 3. And do you know what 1 over the square root of 3 is without your calculator? Yeah, I don't either. I could figure it out, but it's a lot of work. So what we're going to look at is we're going to try to graph the easy points with tangent. And we're going to graph the parent function for tangent for one cycle, just like we did for sine and cosine. And then we did the transformations to it, and then we repeat it. Exact same thing happens with tangent. You just may repeat a little sooner than you do with sine and cosine. And I'll show you what I mean by that. So with tangent, there is one big thing to remember, and that's the period. If you remember from when we were solving, tangent repeats every pi, because the period for tangent is going to be pi over b, because it repeats every pi. Whereas sine and cosine, it was 2 pi over b. But again, tangent's period is pi, so therefore it's pi over b. So that's an important skill to remember. So we actually have to graph less. We're still going to graph 5 things, just like we do with sine and cosine, but it fits in a shorter period. So graphing tangent, my recommendation for scales for tangent is typically counting by pi over 4. And the reason I recommend counting by pi over 4, we can count by pi over 6. It's hard though to find pi over 4 when we count by pi over 6. But the reason we like to count by pi over 4 is, what is the tangent of pi over 4? 1. Y divided by x, same thing, divided by itself is 1. So this is a really nice value. So this one's pretty easy. This one's pretty easy. Okay, this one's not easy, but we can do it. This one is easy, 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 not easy, but easy, and easy. So I'm talking about all the way around the circle. Again, we're not going to graph everything around it, but we have some of these nice values, which happen to be at those pi over 4 tick marks. If we have some goofy horizontal transformations, instead of counting by pi over 4, you may want to count by, again, pi over 12, because that takes into consideration pi over 6, and you just count. Pi over 4 is just the same thing as 3 pi over 12. So when you tick mark it out, 1 pi over 12, 2 pi over 12, 3 pi over 12. Well, that's just pi over 4. It's just spacing it out a little bit more so that you can see your graphs a little easier. So when I want to graph tangent, I'm going to erase all this here for a second. What we're going to look at is, I know this is kind of an odd piece, but normally you know how we start at 0 and go around and we graph to 2 pi? Well, for tangent, instead of starting at 0, we actually start at this value, but not 3 pi over 2. We're going to go negatively around. This is negative pi over 2. Remember how they terminate at the same spot? So therefore, the tangent of these angles are the same, but the angles themselves are not the same. So this is going to go in the negative direction. So this is going to be, so here's the xy axis. So this is going to be out here at negative pi over 2. And then we're going to go from negative pi over 2 around to pi over 2. That's one cycle. What's that horizontal length? Pi, because that's the period of tangent. So this is just how we graph one cycle of tangent. It goes from negative pi over 2 to positive pi over 2. Could I go from 0 to pi? Yes, but if I do horizontal compressions or stretches, it just makes it a little harder. So it's typically easier to do this, and I'll show you why in just a second. So if I want to graph this pi area, I need to know what my values are. So I could make a table, negative pi over 2, negative pi over 4, 0, pi over 4, and pi over 2. I can make it that xy table. What I just listed there were all my x's, and then I can find all my y's. So if I divide these out, again, let's clean this up just a smidge. So if I divide these out, what's negative 1 divided by 0? Undefined, not 0, not 0. 0 divided by negative 1 is 0, but negative 1 divided by 0, we can't divide by 0, so that's undefined. And then here, negative square root of 2 over 2 divided by the square root of 2 over 2, something divided by itself but negative is negative 1. 0 divided by 1 is 0. Something divided by itself is 1. And then 1 divided by 0 is undefined. And this is actually why we typically go from negative pi over 2 to pi over 2, because these undefined pieces, think about what happens graphically if I can't have an x value. What happens on your graph at negative pi over 2 and pi over 2? There is a vertical asymptote. So there's a vertical asymptote at both pi over 2 and negative pi over 2, because again, those are undefined terms. There's either a vertical asymptote present or there is a removable discontinuity. So I'm putting those vertical asymptotes in here. Those are 2 of my 5 pieces of information I'm going to graph. So let's double screen here. So then I need to graph all my other values. So at negative pi over 4, that value is negative 1. So at negative pi over 4, let's change our color here. Negative pi over 4, it's negative 1. At 0, it's 0. At pi over 4, it's 1. And then it's asymptote here. Okay, so those are the 3 points in between there that I have to graph. So 3 points, 2 asymptotes. Those are the 5 things that make up every tangent function. Now, keep in mind, there's an infinite number of points through here, and we have asymptote behavior. So what happens is this kind of looks like a cubic. It's not, but it looks like a cubic. So this is that turning point. So it curves through here, follows that asymptote. There's our asymptote behavior. And then comes through here, curves through here, and there's our asymptote behavior. So that is 1 period for tangent. And then what we can do is we can replicate this. My recommendation is whenever we're doing our transformations with tangent, we get 1 tangent graphed with the period, replicate it, and then do everything else with it, specifically our asymptotes. So from here to here, horizontally, if you look at your distance from negative pi over 2 to pi over 2, if you were to subtract pi over 2 minus negative pi over 2 is pi. So that horizontal distance there is pi. That's why the period is pi. So every pi out, we have another asymptote. So count boxes. How many boxes are there between the asymptotes? 4. So therefore, 1, 2, 3, 4. There's another asymptote. 1, 2, 3, 4. There's another asymptote. And I do this in both directions. 1, 2, 3, 4. I'll just go 1 negatively. Okay, so now once I have my asymptotes, I know these 3 points always are the same. Halfway between the asymptotes is 0. Halfway between 0 and the asymptote is 1, and then negative 1. 1, negative 1, 1, negative 1. And then draw those curves. Pardon the not so good curve. But that's your parent function for tangent. Again, this keeps repeating itself, and we will just assume the pattern keeps going. You don't have to do anything because that's the downfall to the asymptote is it kind of stops it, but we will continue that pattern through. So we're going to do one with a horizontal transformation because that's really the hardest part to it. All the rest of them I'll talk about after we do this horizontal one, but they all follow suit exactly the same. Okay, so first things first, b is 2. That's b. That's between the trig function and x. So b is, in this case, the number of full cycles that fit between 0 and pi, because pi is the period for tangent. So therefore, the period for this function is pi divided by b, so pi over 2. So before, our period was pi. It was pi over 2 on each side. That gave us a total distance of pi. Now, the whole distance between those asymptotes is pi over 2. So let's scale this out. Again, I'm going to count by pi over 4s. I'm just going to mark every pi over 2 so it doesn't get so messy. So here's pi over 2. There's pi, 3 pi over 2. But again, I'm counting by pi over 4. 1 pi over 4, 2 pi over 4, 3 pi over 4, 4 pi over 4, etc. So negative pi over 2, and then negative pi, and maybe negative 3 pi over 2. Again, I just want a graph between negative pi and pi. I won't worry about that yet. I need to do one cycle. So since the period for this scenario is pi over 2, I know that half of it falls on each side of my y-axis. So that's why it's easiest if you use both the negative and positive side, because half of it's on each side. So keep in mind, pi over 2 is 2 boxes. So the whole thing is 2 boxes. So therefore, it goes, it goes from negative pi over 4 to pi over 4. That's where one full cycle is going to fit between, because when I count these, that's 2 boxes. That's the horizontal length of the period. And then once you know your asymptotes, you can just plot your points. Middle is 0, middle is 1, middle is -1. So keep in mind, these are not on tick marks. That's fine. That's why some people want to count by pi over 8 or pi over 4, some of those changes. But this is going to be a horizontal compression. So that is one period of pi over 2 with a horizontal compression of 2. I asked you to graph from negative pi to pi. So now I have to replicate this, getting out to pi and back here to negative pi. So that asymptote is every 2 boxes. So therefore 2 boxes later, I have an asymptote. Oh, I cannot get those straight. And then another 2 boxes is my asymptote. I know it goes past pi, but I'm just going to put it in there just for the time being as a placeholder, and then I'll delete it. Because I changed my domain, I need to, or I was specific with my domain, I need to make sure I follow the rules. Okay, so there's all my asymptotes. And then go ahead and plot those points in the middle. Okay, and then here, I'm not going to do past negative pi because our domain was restricted. And just make sure we can see your points. I know sometimes it gets hard because everything's so scrunched. On your test, most likely you'll have a nice amount of space. Oop, I went past pi. Okay, so let's erase everything past my domain. Well, I guess I'll erase the numbers too. And then I'm also going to delete those asymptotes. Oops. Okay, so therefore it goes from negative pi to pi based on this. So if there is a vertical stretch, we're going to multiply. So 1, say it was 3, 1 goes up to 3, -1 goes to -3, 0 times 3 is 0. So again, we do all of our stretches and compressions first. And then if I have a vertical shift, this value here that's in the middle, that midline is going to shift up or down. So that's that turning point. So I'm going to look at where does that like cubic-ish shape, where does it go from concave up to concave down? Where does that shift up to? And then if we do anything shifting left and right, do that again last. That's at least my recommendation. And then I'll just double check to see, okay, did you get it in the right spots? Okay, so that is graphing tangent. Not super special about it. Just initially it's a little harder because of how we have to come up with tangent, but the shape will always look the same.